The Bode plot capability of the Siglent SDS1104X-E Oscilloscope paired with a Siglent function generator can plot the magnitude, ratio, and phase relationship of two voltage inputs over frequency. Impedance is just the voltage divided by current, and admittance is the ratio of current to voltage. So if we use a current probe to convert current to voltage, that enables the Bode plot function to directly plot impedance or admittance. So this is the setup I'm using. I'm using my Tektronix P6042 Current Probe. The amplifier's here, the probe is here. I bought this 30 years ago at the TRW Amateur Radio Swap Meet. It's probably about 50 years old. Now the Siglent scope and the function generator I've bought within the last couple months, and both of those are plugged into an EDI Max wireless router that's configured as a range extender, so I can hook into the Wi-Fi network in my house from the garage. I'm also using the Siglent PP510 10-to-1 probe that's supplied with the oscilloscope. And over here I have a Dur EE DE5000 LCR meter that I use to check the impedance at spot frequencies of things I was measuring to make sure stuff was coming out correctly. So my initial measurement was a 10 ohm low inductance resistor, a power resistor. I've used these in projects, and they're essentially good resistances up to the low hundreds of megahertz. So I hooked this up. I hooked set the current probe to 50 milliamps for 50 millivolts, or a gain of 1. So that I don't have to do any conversion, and just ran it into the scope and did the measurement. And so I plotted the magnitude and phase and then I converted the impedance from the dB value like this. You divide the dB value by 20 and raise that to the 10 power. And I got 9.3 ohms, which is low because I know I've measured this resistor, and even though it's 5%, it was really 10.02 ohms. And it should be flat out to the low hundreds of megahertz, and here I'm seeing a lot of phase shift at starting in the hundreds of kilohertz, and a lot by the time I get to 10 megahertz. That's just not right. So I thought, well, let's measure the current probe. So I'm doing a very simplistic measurement here. I've put a wire loop on the output of the function generator. I set channel 2 of the function generator up to duplicate channel 1, and that goes into a 50 ohm terminated input in the scope. And I plotted the response. So if you make a very simplistic assumption and ignore the inductance in that loop that the current probe is measuring, as well as any impedance the current probe adds, you would expect to see a flat line here at minus 27.95 dB. And a flat phase response. And so if I look at what I'm getting from the current probe, I see that in fact the gain of my current probe is a little higher than what I expect. And since it's in the denominator, that means the value of the current is showing up as a little bigger than it is. That would make the impedance measure a little low, which is what I saw. So now if we look at this magnitude plot, we see little jumps in the magnitude plot here. The biggest one is perhaps this one here. Now what these are from is the way that the Bode plot function in the scope works. It does its best to match the size of two waveforms by adjusting the coarse and fine attenuators of each of the inputs of the scope. Now the attenuators are not perfect. There is error in each one. Now these jumps look big, but that's just because of the scale. If we look over here at the scale, each division here is 1/10 of a dB, and the biggest jump is less than that. Most of them are around 0.05 dB. And those are small, so these errors, although they look big on this scale, are pretty damn tiny. The scope's doing a good job. And these small errors, if you were looking at a waveform in a scope, you would never notice these. The only reason we're seeing it is because of, we're looking at this gain, very fine detail in this gain response. So I can take that gain response and make it a correction factor. So here, this is the gain correction factor, and this is the phase correction factor, and I add this to whatever I measure. So now I take this and I add it to the magnitude and phase of what I measured for the resistor, and lo and behold, it comes out exactly 10 ohms. So that gain error was the reason the resistance was coming out too low. So what you do, you add that gain in phase, and then you derive the impedance based on that corrected value. Now the spreadsheets I've done this with are available for download, so you can see the details of how I did this. Now one thing here, if we look out here, we see that we're starting to get some phase and gain error at 10 megahertz, because I know that these resistors are flat out to 100 or 200 megahertz. So, and that's because of the very simplistic current probe calibration I used, which doesn't account for the inductance of the loop or the impedance of the probe. So now here, this is a resistor that I've been using for many years as a load for testing audio power amplifiers. I never really knew if it was flat over the audio region. I just kind of assumed it was. It's nominally 4.42 ohms, but when I measured it with some Kelvin clips, it came out slightly low, but well within the 1%. And if we look at it over the audio range where I use it, well out to 100 kilohertz, it's flat. So, and especially, there's even no phase error, even at 20 kilohertz. So as a load for an audio power amplifier, it's a good test load. Now let's look at the impedance of a speaker. This speaker I pulled out of my Ford truck quite a few years ago, and when I replaced them with some better speakers. Now here I'm doing the impedance measurements two ways. One with the speaker face up, and the other with the speaker face down. So first let's look at the face up. Nominally it's 4 ohms. Here's 4 ohms. This is 3, so this is about 3.66 ohms here. And we see a very sharp resonance at about 70 hertz, and then that drops down. And then the impedance slowly rises over the audio range and then starts to shoot up above audio. Not shoot up, but rise at a steeper angle. Now if I flip the speaker over and point it face down, the first thing you'll notice is that this impedance here at 10 hertz has shifted up a little bit. Not a lot, but maybe from 3.6 ohms to 3.8 ohms. And the other thing you'll notice is this resonance here at 70 hertz is gone, and it's moved out to 200, 300, 400, 500, 550 hertz about, and it's much smaller. And you can also see here the big phase response we had at 70 hertz. We get a similar phase response here at but it's smaller. So, as is true with most audio transducers, their impedance and response is very dependent on the audio environment they're coupled to. So if you put this speaker in a door where it was designed to be, you'd get a different response. If you had that door open or closed in the car, the response would be different. And that's very typical, and that's now with this, it's very easy to measure and look at that response. So now let's think more about what we're doing with the measurement. So for a measurement with a current probes like lots of current. They don't like measuring tiny currents. So to get lots of current, we basically turn the function generator up as high as we can. So this is the way I set up the function generator in the Bode plot on the scope. I set it to 5 volts peak to peak into a 50 ohm load. So when you set it for 5 volts peak to peak into a 50 ohm load, the internal swing in the function generator is actually 10 volts peak to peak. Because if this is 50 ohms and you have a 50 ohm resistor here, you'd get a 50% voltage divider and get 5 volts peak to peak across the load. So that's what this means. So if this is shorted here, I'd have 10 volts peak to peak going into 50 ohms going through a short. So at low impedances, I'd see 200 milliamps peak to peak a signal. Now, if this is a very high impedance, this current becomes very low, and whatever voltage I have here, 10 volts peak to peak, is what I see over the device I'm measuring. And that's what this graph is showing. This is current versus the, down here is the impedance that's being measured. This is current, and the current is read off of this scale, and this line here is voltage, and the voltage is read off of this scale. You notice here there's two plots, and that's because depending on whether that impedance is resistive or reactive, this changes a little bit right around 50 ohms. But once you get away from 50 ohms, it really doesn't matter whether the impedance is real or reactive. So if we're measuring very small impedances, we're going to get lots of current, but eventually we get to such a low impedance, as we go down in impedance, the voltage we measure will get smaller and smaller, and finally we'll be limited by the noise of the oscilloscope. We can get around that a bit if we, instead of using the ×10 probe, use a ×1 probe. We can probably get a decade lower, but that introduces other issues, which we'll talk about in a subsequent chart. Likewise, here is if we go to high impedances, let's say 10 k ohms to 100 k ohms, up here, the voltage across the device is going to be 10 volts peak to peak. And as we go up in impedance, we're just dropping the current through it, so the current we measure. And eventually, as we get up to around 100 k ohms, that current is going to be so low that it'll be limited by the noise of the current probe. So one of the things you can see here is we're putting in a pretty big signal, 200 milliamps peak to peak at low currents, at low impedances, 10 volts peak to peak at high impedances. So you're probably not going to be able to use this to measure the input impedance of an amplifier. You'll overload the input stage of the amplifier. So this is really limited to passive devices that can take this kind of signal. And that's almost every passive device, with maybe a few exceptions for very low-powered ones. So as you saw from that last graph, is we want to maximize the signal to increase the range of impedance we measure. So instead of setting, like I did before, setting this to the current probe to 50 milliamps for 50 millivolts, I moved it down to 10 milliamps to 50 millivolts. And I picked this because this is the most sensitive range I can set the current probe on that does not clip. If I go to a more sensitive range, it clips, and then my measurements don't work. But this is the range that gives me the greatest range of measurement. And so here I make a new correction curve, and the correction curve includes the 5x current gain for the setting of the current probe. And so now I'm going to add this to my measurements. Again, you can see this in spreadsheets that I've attached. So now let's think about what's the actual range of impedances we can measure. If we think about it, we have the signal from the signal generators coming in here, and then flowing through the current probe, and then into our device under test. But with our device under test, we also have the scope probe in parallel with it. So we have 10 megohms in parallel with 18 picofarads. The 10 megohms is up here. It's not really shown. But this 18 picofarads is going to limit the large impedances we can measure as we go up in frequency. And so the magnitude impedance of the probe is here. And in reality, we want to be about a decade away from that to get a clean measurement. So really, although the probes, this is 18 picofarads, we want to use the line for 10 times larger, 180 picofarads. And so we need to stay below this line here to get a good clean measurement. Now the other issue we have is inductance in series with the device under test. So essentially lead inductance. If you put the probes right up against the device we're measuring, you're going to get about a nanohenry of inductance. It's going to be almost impossible to get below that. If the probes are almost any distance away from the device, you'll be on the order of 10 nanohenries. And without too much trouble, you can get up to 100 nanohenries. And so you can see that's going to limit the actual smallest impedances you can measure at high frequency. And these are essentially, if you're not careful, these will show up. These are really soft numbers because these are not fixed. These depend on what you do and could show up in your measurements. But you have to be aware that this can happen. Now, one of the interesting things is that there'll be a little bit of stray capacitance between this point and the low point or ground of the device we're measuring. And there's also stray capacitance outside the probe over here. All that matters is this capacitance inside the probe, because any current that passes through the probe, you can get some current through that capacitance, and the current through that capacitance will screw up the measurement. These stray capacitance on the outside of the probe does not matter, because it's not being sampled when we measure the device. And the other thing that means is we really want to move this probe as close to the device as possible, and we want to keep this capacitance under about 1 picofarad, less than 1 picofarad, so it doesn't affect this much. So now if we look here, I'm measuring a capacitor, but you can see the probe leads the scope probe leads are right up against the device itself. And then the leads from the function generator are connected after that. And then I have the current probe as close to this as I can get. Now, from here to where about the tip of the scope probe is over to the current probe, it's capacitance from this over to this area that can cause problems. But if you keep a nice neat layout like this, don't cross anything over here, keep this short, this is going to be under the picofarad, probably in the hundreds of femtofarads, but not in an area that's going to bother us. If you move this probe up, the capacitance is going to increase. The other thing you need to do is keep these leads coming out of the function generator short. If you make them longer, you can still get measurements, but the inductance in here is going to screw up your measurements at higher frequencies because it or reduce your dynamic range. So you really want to keep these short. So now here's an example. I have a Sprague 0.1 microfarad high voltage ceramic capacitor. And here I'm measuring two cases. One where I have the scope probe leads right up against the part, and another case where I have the scope probe leads moved away from the part. So we can see here when the scope probe leads are right up against the part, we get a resonant frequency of about 4.3 megahertz. And this is a real resonant frequency because this impedance is way down below this line. So this is, because this is a 0.1 microfarad capacitor, so the capacitance of an 18 picofarad probe isn't going to make a bit of difference. Now, if we move the leads out here for the long leads, this resonance moves down to 4.3 megahertz because we've added additional inductance. So the impedance is in magnitude and phase. You can then calculate the real part and the imaginary part of that. The real part is the equivalent series resistance, and then the imaginary part is the reactance. If the reactance is positive, that means it's inductance. If the reactance is negative, it's capacitance. And so we can take those calculated values and plot those out. So we can see here that this is the capacitance in both cases, and it's coming out almost exactly at 0.1 microfarads. This is the resistance, the equivalent resistance, and because it's very noisy up here, and then here we're getting a glitch, but that's really, if we look back here, you see this little phase glitch. That's again one of those attenuator issues within the scope. This isn't real. There's a little glitch here between 2 and 3 megahertz. I think this is due to something in the scope probe. Not the scope probe, the current probe, because you'll see this glitch in this range in a lot of the measurements. But now if we take a look at the calculated inductances we got for short leads, it's coming up about, it looks like it's going to level out about here, or about 10 nanohenries. For the long leads, it's leveling out about here, which is about 55 nanohenries. So the difference between these two is 45 nanohenries. So moving the scope probe leads from right up on the capacitor out to here added about 45 nanohenries of inductance. And that's on what I showed you on that chart before on the impedance. Now here is a 5600 picofarad capacitor being measured. This is a nice measurement. Not much to say about this. Now it's a small value of capacitance, so when we get down here below about a few hundred hertz, we get a lot of phase noise and magnitude noise. But again, that's because, remember, this was the limit I had on that chart, and here the current signal is so small that this is just, we're kind of in the noise here. When we get into the range of impedance, we can measure. It's a nice clean measurement. Now here's an example of a 5 millihenry iron core inductor. So you can see here the impedance increases with frequency, as you'd expect from an inductor. It hits a resonance, then back down. Now the resonance crosses over this 180 picofarad line, but I wouldn't worry about that because you're going to get a peak, but these other lines are well out. Again, now we see a little glitch here in the phase, and here between 2 and 3 megahertz. Again, I see this in a lot of the measurements, and I think it has something to do with the current probe. Now, if we look, we recalculate this, and so the impedance, if we look at the inductance, we can see it's a fairly flat inductance out to 10 kilohertz and almost to 100 kilohertz. And then the capacitance, once we get past the resonance, is say 300-400 picofarads. So that's probably real. But we see here that the resistance actually rises steadily. It comes up and peaks at about 10K. Okay, and so if you're used to looking at capacitors, you'll see resonant peaks that are dips, because that's a series resonance. In an inductor, you get a parallel resonance, and so you get a peak. And so this peak here is kind of, this resistor would be in parallel with the tank circuit. But you see here that this resistance is rising, and this resistance really represents energy loss in this device. And I'm not positive, but because this is an iron core inductor, I suspect most of this energy loss is in the core itself. Now I want to measure an electrolytic capacitors. Now electrolytic capacitors require a DC voltage offset to measure, because you don't really want to reverse bias them. And that's especially true of tantalum capacitors, because you can permanently damage many tantalum capacitors with any reverse bias. So this is how I set the function generator on the scope in the Bode plot function. I set it for 4 volts peak to peak with 2 volts offset into a 50 ohm load. What that really does is it applies a 4-volt DC offset, and if you have a capacitor here, it will put 4 volts on the capacitor, and at most there'd be 8 volts peak to peak across the device, so it would never swing below ground. But when we're measuring an electrolytic capacitor, we tend to have low impedances, because that's why we're using them. We're using an electrolytic capacitor to get a large capacitance value in a small package. And so you're mostly going to be down here where this voltage swing is small, even smaller, and will never even come anywhere near ground. So now let's look, here's an example of a measured electrolytic capacitor, the 220 microfarad 25 volts. So here we see this glitch right at the beginning of the plot, and this is kind of a glitch in the Siglent Bode Plot software in this, or firmware in the scope. It's fine during the first sweep, and then it'll screw up this first point, and on the subsequent sweeps sometimes it'll go back. It's not a huge deal, but it is a little annoying. So here we see the impedance drops, and then it kind of levels off. We have the ESR, then it comes up and where it starts to look inductive. Again, we have one of these glitches in the 2 to 3 megahertz regions. That glitch is not real. So if we convert the measured impedance to capacitance and inductance, we can see here this capacitor has a fairly nice, well-behaved resistance all the way through resonance, and it's got a series, an ESR of, what's this, 0.1, call that 0.12, 0.13 ohms. Very respectable. It's 220 nanofarads or microfarads nominally. If we look here at low frequency, yeah, it's looking 230, 240. If we get up to 10 kilohertz, it's dropped to about 190. But it's staying pretty close, at least through the audio range, and then it starts getting near resonance. Now, once we get through resonance, we can see here, this is the inductance value. And if we come back over here, this inductance, the self-inductance of this capacitor is on the order of about 30 nanohenries. So the conclusion, the Tektronix P6042 Current Probe, Siglent Oscilloscope, and function generator used together are capable of making very useful impedance measurements. The results are good from 10 hertz through 1 megahertz and useful out to 10. No special fixtures required for measuring leaded components. The measurements are very slow, which is why I didn't show me making one on this video. It's be as interesting as watching grass grow. And so it's really not suitable for a production environment, but it adds great capability for a home lab. I'm thrilled to be able to measure impedances curves in this range. I've never had that capability before. I think it's pretty cool. Okay, the simplistic calibration I used has issues above a few megahertz, but seems good enough for these measurements. Anyway, I'll plan on doing a future video on characterizing current probes, which will include the de-embedding of the calibration circuit and the probe insertion impedance. But that's a much deeper rabbit hole than I was willing to go into for this video. Anyway, you should download a copy of the PDF of the charts from the links included in the description. Besides the charts you've seen here, I have many more examples and equations in the appendix to those charts that will be very helpful if you're trying to understand what I did. I also have some of the spreadsheets I use to generate these graphs and do the corrections so you can follow what I did in detail. If you like this video, please give it a thumbs up. And if you'd like to see more videos from me, please subscribe. Anyway, thank you for watching.